Welcome everyone. This is an edition of the EasyPower Thursday webinar series. Our mission is to bring an array of information pertinent to various parts of our industry from various sources. Today's topic is utilizing the EasyPower harmonic analysis capabilities to troubleshoot issues predominantly caused by power factor correction. Now, this is not meant to be an exhaustive probe into a widespread problem. The direction I'm taking is to discuss the process of anticipating and or determining the problem areas in a system and the use of the EasyPower Harmonics module in that pursuit. It's not meant to be anything detailed as far as harmonic filter design. It's meant more to be food for thought on your part in addressing problems with your clients. So the topic of harmonics and electric power distribution tends to cause those of us with short attention spans to doze off. So I thought I might start with a bit of history lesson to bring everybody to the present date and not necessarily get bogged down in the technical parameters just yet. So a little bit of the backstory. When Edison and Tesla parted ways, much of their disagreement was based upon whose methodology for distributing electric power was better. And Tesla basically took the position that if we use transformers and an AC distribution system, we would have a more efficient delivery of power and energy to the end customer, and they could then take that transformer and take the voltage down to a level that they would be using it as a consumer. So harmonics were known to occur in AC circuits at the time, in particular when transformers were energized or if you had physical anomalies in the rotating machinery or generators. But for the most part, harmonic content was very low compared to fundamental voltage and current values. Well, over time, AC did become the standard for energy distribution, and over the course of time, the standards became pretty much a 60-cycle distribution system in the Western Hemisphere, or most of it, and 50 cycles in most of Europe and Asia. And as I understand, even Los Angeles was devoted to a 50-cycle distribution system up until about 1945. And then Japan actually has distribution both at 50 cycles and 60 cycles. A little bit of trivia. And over time, as distribution or electrification of the world became widespread, motors of all sizes tended to dominate the position as end load in equipment. By 1995, it was estimated that over 1 billion motors were in use, and there were over 40 million in industrial manufacturing operations, consuming 70% of the total electrical energy in the typical manufacturing plant. It was also estimated that at that time, as much as 38% of that energy was considered wasted. In the US alone, it was estimated the industry spent $30 billion annually on motor systems energy cost. Well, the issue became one of getting that much energy out into a consumer base that was growing, but the cost of expanding the grid became somewhat untenable. And the end users didn't want to pay for this wasted energy. They just wanted to pay for the energy that was delivered that did work. Well, the fact that the higher motor usage requires reactive power to be supplied to provide that real power provided something of a dilemma. Now, the analogy that I like best in terms of describing what reactive power is compared to real power is the story of a horse who was pulling a railroad card, and the track that was the horse had to go on was removed or moved to the side. And so to be able to produce a forward effort or forward motion, the horse has to apply some energy to the side, which does not really move the carriage. And so the analogy is the apparent power, which is the total force the horse has to apply, results in real power, which is motion of the carriage, but also the reactive power, which is the strain on the horse because he has to pull at the angle. Well, in more technical terms, the reactive power and when the voltage and current are both in the same phase, as they would be in a resistive load, the power factor is considered to be 1. But as soon as the voltage or current has to change phases because of this response to the reactive demand of the loads, we have a change in power factor. And for the most part, with the inductive loads, we have the current that actually lags the voltage, and it's that need to provide reactive power at the point of supply that the utilities were having a problem with. So in an effort to encourage people to be more efficient, the utility companies came up with the idea of assessing power factor demand penalties, and consequently, if I had a facility that had a lot of motors and I didn't do anything about it, my penalties could actually increase my utility bill considerably. So industry's response to this was to put power factor compensation circuits inside the plant or inside the facility to reactivate or recycle this reactive current and thus relieve some of the strain on the utility. So for the better part of the 1980s, the battle cry, or at least the vogue in power quality circles, became the promotion of power factor correction. So over the last 20 years, power factor correction was promoted, in fact, as the green solution with the shortest payback over anything else. What it amounted to is that inside of my plant, downstream of my point of connection with the utility, I would install basically power factor correction capacitors, which allowed the reactive power, once my capacitors were charged, to recycle inside the plant, and thereby eliminating the need for that reactive power to flow back up or in and out of the utility connection. Also, it actually involves some significant power saving or energy savings, because that extra current, even though it was reactive, didn't have to flow back and forth through the utility pipeline, if you will. And even inside of my own plant, if I located the power factor correction near the large motors that were drawing or creating the reactive demand, it reduced the losses inside of my plant as well. Well, at the same time, technology came of age, and in the 1960s, silicon-controlled rectifiers have evolved or became cost competitive at the time to be considered as drives for DC motors by rectifying the AC current. And in the 70s, we saw increased integration in semiconductors and the development of phase lock loops, which made it easier to synchronize and have higher integration of control systems to be utilized in motor controls. And then since the 80s, we've seen the evolution of bipolar pulse width modulated systems and insulated gate bipolar transistors, which allowed industry now to develop smaller drives, and what at one time a 10 horsepower motor could have weighed 30 or 40 pounds and taken up a fair amount of space, now becomes small to the point that the same amount of torque or energy could be delivered to something that can be carried around in one hand. So as a result, technology has offered real savings, and that improved efficiency really means now that more energy is being utilized or used, and what we see in buildings that have been designed even as late as 10 years ago, but certainly before 15 years ago, in their design plans, they were expected to handle or encounter only 60 cycle systems. They're now being exposed to a wide spectrum of harmonic content, and the dilemma was unavoidable. This harmonic content is not just from motor controllers, but from a vast array of other nonlinear loads. So this begs the question, today, when should harmonics be discussed? Well, certainly at new designs, or when the plant's being originally designed, it's obviously a time that we need to be considering what the harmonics are that will be within the plant structure. Likewise, if we're making changes to an existing system, we need to talk about in terms of motor control contributions or system sensitivity to existing harmonics. And pardon my rashness, but what other appraisal of the system does these data points coincide with? What is the basic analysis tool for the planning, design, and operation of any electrical system, be they industrial, distribution, or transmission networks? And of course, the answer is power flow analysis. Yeah, that's right. At each of these intersections, we should be doing or want to, our primary objective is to make sure we have a safe and sound system that can operate properly and accommodate the capacity required by the plant's occupants. Now, all this comes to bear if we start having problems in a system, and having a power flow analysis available puts us one step ahead when it comes to talking about harmonics. Better still, if you have a power flow model that reflects the normal operations of the plant, including harmonic content, let's call it the harmonic signature of the system, then the task of troubleshooting becomes simpler when things change. So this brings me to a couple poll questions, and I beg your patience here, but I would appreciate some feedback. Specifically, how often do you or your clients conduct load flow analysis, and how frequent, whether you do it for them or whether the client does it themselves? Obviously, there's no obligation to this. I'm just trying to get a feel for the audience, and also how sensitive everyone is to this particular dilemma where we're anticipating having to solve problems as they arise. And here's how folks responded on this, which is admirable. And then the second question is, how often or how frequently do you suspect a harmonic problem and have a problem really knowing where to start as far as solving the solution? I appreciate that feedback and your participation. Let's kind of jump into a more detailed discussion now of where we're going with this. So now, as you would understand, having a load flow study, especially if it's current and certainly something within the last year, is manageable, although there was a time, just to kind of date myself, when load flow studies were kept current almost to the week. And it was the yardstick by which we could track trending maintenance problems or anticipate failures before they affected production. So having a load flow study complete and up to date is a big part of it, because from that, if we have not done modeling that includes harmonics, from that we can add in the harmonics contributed by each load, and it will be affected by or the tools can anticipate or compensate harmonic contribution based upon the power flow and percent usage as far as capacity. And then by utilizing that, the process would be compare what we are measuring in the system compared to what's being predicted by the model. Now, harmonic problems can manifest themselves in elements that are overheating. Frequently, we can see circulating current in delta transformers because of high harmonic current in the neutrals. We can see capacitor failures, intermittent trips and relays that really don't seem to be explained by the data logging that may, as far as the power usage. Motor generators or negative sequence operations. Quite literally, in a severe case, we could see reverse rotation. Total power factor could tend to be worse, and especially if there's a potential for having frequencies in an area of resonance of the system itself. Bottom line is, many of these problems are tough to pinpoint, and frequently the harmonic analysis is the last point of a solution because we've tried everything else first. So, as you would expect, the harmonic analysis really requires a two-pronged approach. A review of these parameters are in part the initial facility design and commissioning. And as I say, if you have a signature of what the plant looks like on a harmonic basis on a day-to-day normalized measurements, it's much easier to pinpoint where things have gone awry. Now, in part, as we do our studies under normal conditions, we want to refine the system model, identify and verify the harmonic sources, and if we're approaching a situation where we don't have the history of that, the first attempt is going to be to try to understand what the measured harmonic distribution is compared to what the predicted model distribution suggests, and then verify where those differences occur. More difficult, again, if you don't have the initial study or initial harmonic signature. So in the harmonic model, we need to identify the sources. Frequently it'll be VFDs, rectifiers, loads that have harmonic content, and in the EasyPower tools, they're modeled as a current source with infinite impedance. Motors and generators can be contributors and sinks. They're modeled with as a sink with shunt impedance, and then potentially subtransient impedance as an additional load. And then loads that do not generate harmonic content are identified as a sink and have a tendency to temper some of the frequency of responses. And in the model, the utility is going to be most often modeled as a sink with Thevenin impedance, unless we can get the frequency distribution from the utility company. And then in cables and lines, there's going to be series impedance and cables that basically have a filter function to them, and they're modeled as a pi model. So there's three approaches or three faculties that the EasyPower harmonic module offers. One is a summation simulation, where we do the summation calculations of total harmonic distortion, both current and voltage. We can compare those results against industry standards and limits, determine equipment derating requirements, including transformers, cables, and other system elements, and then look at standard levels as far as RMS and RSS and reports, and then in the final analysis, specify where the predicted losses are throughout the system. Then beyond that, we will get into harmonic current flow, both single source current injection, and there we're looking for the system response to specific harmonics. The default setting is the fifth harmonic, just because it's most frequently generated, and as you'll see, it's most sensitive in a power factor correction environment, but that can be customized to any particular harmonic that we want to analyze. And then there's a capability of doing an all source current flow, which determines where all contributions and which buses are most affected when all the harmonic sources are included in the analysis. And then thirdly, we can do frequency scans that again utilize single point current injection and can scan a vast array of up to 50 harmonics that we can anticipate or detail what the response at each bus is. And frequently this is where you'll be able to locate the potential for resonance. And then as a jumping off point, we're going to talk about the reports that can be generated. So let me kind of jump out of this into the tools. Now I wanted to highlight my example here as an extreme demonstration case meant for dramatic purposes, not for anything of specific nature. And in particular, I've got a 1,000 horsepower motor on a 480 volt bus, not usually something you'll see in real life. But with that said, let me kind of walk through the storyline that I just laid out. So first of all, we have a one line diagram, and most of our loads, all of our loads, let's say, are linear. And so what we'd see as we go into power flow is the ability to solve or resolve both the real power and reactive power demand. And so when we apply or have this large motor in our system, it draws a fair amount of current and has a tendency to cause power factor to drag considerably away from unity value, which the utility company most favors. So in this particular case, I'm showing a power factor of 0.80, and in most venues around the country that would incur power factor demand penalties. And so the solution at the time was to include or put in power factor correction capacitor banks, usually in close proximity to the loads that were generating the demand. And what we can see here, just as an example, we're displaying the real power and reactive power that has to be delivered to the motor for it to be able to run at its performance level. So there's two reasons to put capacitors in the circuit. One is to correct the power factor itself, and the other is to bring up the voltage, because with this load and the losses involved in the system, the voltage is going to droop to the point we have a less efficient motor operation because of the low voltage. So the solution at the time was to put in power factor correction. So as I bring on this capacitor bank, what I see is now my voltage is brought up to 99 per unit, 0.99 per unit. My reactive power demand is cut by 90%. I can see that my utility power factor now has gone up to 0.98, and the utility company will be much happier. I get a much more efficient use of the motor now, and everybody's a happy camper. Well, that was all well and good until we started adding things like nonlinear loads. So now if we add a rectifier, let's say in this case, and for that matter, let's change out my motor to a VFD drive. And to do that in EasyPower, all I have to do is indicate that it's a VFD. It really doesn't change my short circuit model, but I have the ability now to include harmonics. And let's say this is just a typical industrial motor control, and let's say it's pulse width modulated at 100% load, just for a starting point. And so now what this does is import, if I had the measurements from the system or if I had the data sheet from the manufacturer, I could input the harmonic generation or the predicted generation based upon whatever the current level is we're running. Failing that, I'm going to go with the typical values that the tool has within it, and we'll import these into our model. So now when I go back to power factor, power flow, and solve, I can see that we actually have a reverse situation, because now there's not nearly the reactive power being demanded by the motor, and with the capacitor still in the circuit, I'm actually generating a reverse condition where I'm supplying reactive power out to the grid. Not something that the utility normally likes, as long as I don't stray, but they'll potentially live with it if I don't stray too far from unity. Nevertheless, the question is, what does that do to my harmonic distribution in my system? So if I go to the harmonic module, which is this icon here with the different waveforms, I want to look at the summation of harmonic distribution. And so I'm showing on my voltage distribution, VTHD is at 56%, and I'm seeing 13% on my total current harmonic distribution, and 110% again with this capacitor in place. So at very least, if I take that capacitor out of it, I can see I'm back down at 13% harmonic distribution for current, 13% harmonic distribution for voltage. Still exceeds my 5% goal, but it's better than we started when that power factor correction was in place. So this brings up the question, what else is going on, or what other concerns should I have other than just removing the power factor correction bank? So what we're looking at, if we notice this top series of buttons, is the VTHD and ITHD, again for all the system. I can identify it for individual bus, and we can generate reports that show the summation and detailed for any particular standard that we're looking at, including summary reports for IEEE 519 losses and a derating for different pieces of equipment. So let's go ahead and apply this and look at the report results. So my summation detail report shows my harmonic distortion for voltage and the branch flow distortion for each of the currents. And again, what I'm looking for is anomalies that are large on a particular bus and vary from what the expectation is or what's being measured. Likewise, the comparison report for the summary shows the summation reports, the transformer derating reports, the conductor derating reports, and the branch losses. So that's on the total summary scan. A lot of information, and again, it's something I would make a point at this time that you can download the EasyPower tools that include this capability. And if you go to the, let me just show you this. If you go to the tutorial page, there is listed in the center column of the start page the ability to do harmonic analysis, and there's a step-by-step tutorial that shows on-screen stages and will take you to the sample folder that already has the drawing set up for doing this study. So I'd encourage you to do that if you have an interest in learning more about the harmonic capabilities. Now let's go back to now I'm ready to do my frequency current flow analysis. And so the first thing I want to look at is my frequency distribution on a bar chart. So as I select this particular bus and plot a bar chart, what I see are the currents and voltage, in this case the the voltage distribution based upon the different sources that I have coming into the bus. And I can see right here fairly heavy dependence or heavy contribution from something near the fifth harmonic. Likewise, I can look at any bus or any branch to see what the distribution is of the frequencies. If I choose a branch, it'll give me the current contribution. In this case, this looks relatively small on a per unit basis. Obviously, it'd be different if I look in my heavy motor. Now, so what we're showing here, and I set this up intentionally on my display. If I come up and look at my harmonic options, my plot output, I've intentionally excluded the fundamental. If we start with that, it actually kind of overwhelms the plot, but it gives me an idea of what percentage that particular contribution is responsible for. So this, clearly would be something that's a problem and requires mitigation. So that's a starting point. Now, not to make it seem easy, the point is, and that's my whole reason for being an exaggerated example, many of these factors will be nuanced and contributions may be coming from multiple sources, and that's why you need to do a combination of test and simulation to verify what if, because clearly you could have problems more than just the power factor correction, and you would be wise not to jump on the first obvious solution and make sure that you're not missing something that's covered up by at least your initial analysis. Then finally, I want to do a single point scan, and so I'm going to pick out the bus. And again, here we're scanning with the 1 cycle per unit at the fifth harmonic, and it appears to be a fairly linear solution as long as I don't have that capacitor. As soon as I have capacitance in my system and I look at a scan, I got to select the bus. If I do a frequency scan at that point, there's very obviously a resonance, and that's what we're fighting when I just throw and it's a seventh harmonic. So back in the day when power factor was the vogue and I threw this on my system, it may not have caused problems if I didn't have any harmonics floating around in the distribution system. And that's why the error or the problem arises. Now if we put VFDs in the system, do they generate any frequencies that coincide with that particular resonance? Now, just while we're here, I'm going to talk a little bit about mitigation. The first thing, frankly, that you do is not just throw another filter on there. You want to look at other potentials, and if the cause is the controllers and pulsing of different large motors, there are methodologies and steps to take that give you more flexibility rather than just throwing on a filter. But with that said, let me talk in terms of how to try a filter and see what the results are. So what we're looking at here is in my database, I've added a filter to the system from my equipment palette, And I've come up with some parameters for a typical notch filter for the kind of frequencies we're looking at. And so we're describing the inductor, complex impedance, and a capacitor bank, if you will. And we want to see the effect of that, adding that filter into my harmonic analysis. So if we put in our summation, we're seeing 13% distortion in voltage, and in the current distortion we'll see in 25%, as much as 25% in this particular motor. You put the filter in line or in the system, it drops my total voltage distortion down by half. If I take that back out, it drops it from 13.3 down to less than 7%. So that tells me I'm not within my 5% goal, but it certainly is a step in the right direction. If we scan now my harmonic to see where the harmonics, you can see now I brought my my filter down in to trap, if you will, anything at fifth and above, and I have a kind of a soft spot right about 4, and so that may be acceptable in terms of operations of the filter. But if we look at the all source plot, so that shows on all sources that our harmonic distortion is less than 8 volts at this point, and my current distortion, at least in series, is 211 amps, which still may not be accessible, but if this is on an isolated transformer, it might be something that I could live with. The thing I want to look at also is my bar chart on this particular bus where the filter is installed. With the filter installed, I'm going to need to take my fundamental out of there again. So we're going to start to scan it at the second harmonic and plot our bar chart. The thing I wanted to illustrate is that, okay, we have considerably reduced and filtered out the fifth harmonic, which was considered to be the problem. And these others, while they're still present, are much less of a problem because their effect is going to be, resistance-wise, a contribution of the root squared of that particular frequency, of that particular harmonic. So what I wanted to do is to show you the change if I take my filter in and out. So let's take the filter out, and I can see that now I get my fifth harmonic is back in the system. So capabilities of the tools give me the ability to go through a fairly significant span of what ifs in terms of the sources. If I have contributions, if I measure contributions that are not identified, I can include the description of those frequencies of those sources in an element that looks like a rectifier, or just by adding an element in the system that has specific harmonic contributions. I'm looking at the wrong bus. I want to look at the load. So I could go into harmonics and then add in whatever specific contribution I want from, if you will, a virtual source. So then at the point that we're producing reports, we can produce both current flow reports and summation reports. As I mentioned, the IEEE 519 ratings, along with transformers, conductors, and all summary reports. I mentioned mitigation. There are preferred methods, and this is where This is where you need to do your homework. In fact, multi-pulse cancellation is probably the more frequently preferred methodology rather than just slapping in a new filter. And this involves canceling the pulses from different time frames or phases such that you still have the rectification, but the frequency basically cancels out because you have different combination of transformers supplying the pulses. Likewise, you can derate the equipment so that you're not being affected as much by it doesn't change the harmonic contribution, but it does affect, or at least minimizes the negative effects on a piece of equipment if you can detune it or underutilize it. You can convert pulses to a higher pulse count so you don't get as wide a gap, or you get higher frequency production, but it's higher harmonics that don't affect your system as much. You can relocate, surprisingly, because a lot of this resonance is due to physical cabling and physical location of certain pieces of equipment. Sometimes load balancing or even relocating certain feeders can solve harmonic problems. And then ultimately getting to passive filters or active filters can be the recommended solution. So again, where we've gone with this is a discussion on how to go about preferably generating a harmonic signature when a system's commissioned or when a load flow study is done, and especially identifying potential areas that are sensitive to harmonic production, and recording those values or recording that model such that as things change or system capacity is anticipated to change, you can predict what the results and what prevention could be in place before you actually run into problems. And I do recommend, if you have a chance, to download the EasyPower tools and try for yourself the simulation that can be done on the existing one-line diagrams. For those of you that haven't visited the website recently, we've did a complete overhaul, and there's online articles and resources that can be downloaded for free. There's a complete ArcFlash resource page and online training that's available in both PowerFlow and ArcFlash analysis. Thank you all for attending today, and we will be picking up questions and answering via email if you'd like to enter them at this time. Thank you for attending.